Assalamualaikum and hello to everyone. So in this video, we will look at one of the question from the tutorial section for chapter 3 part 1. Okay, so you can pause the video to read and understand the question properly. So in this question, we have a diffuser, okay, where the substance is a refrigerant R134A. Okay, so the inlet condition at state 1 is the temperature 22 degrees Celsius and the phase is saturated vapor, and it leaves at 700 kilopascal, meaning that at the exit state 2 pressure is 700 kilopascal and the temperature is 40 degrees Celsius. Okay, so as the working fluid going through the system, okay, so as the refrigerant is flowing through the diffuser, it is gaining heat. Okay, it is gaining heat, so there is a Q added, okay, or Q in here, as much as 5 kilojoules per second. Okay, so given that the exit velocity is 82 meter per second and the exit area is 1.85 larger than the inlet area, so be careful with this statement here. Okay, make sure you understand, okay, what is the meaning. Okay, for exit area is 1.85 larger than the inlet area. Okay, so we are asked to find or calculate the inlet velocity V1 in units meter per second and also the mass flow rate, okay, of the steam. So we can do a correction here. It's not steam, but actually it's the refrigerant. Okay, so sometimes questions have typing error. Okay, so mass flow rate for the refrigerant, okay, in units kilogram per second. Okay, so we have the answers here, so we can try to do and check on the question and then check with the answers. Okay, so before we start with step 1, let's list down the conditions. Okay, so based on the question, the device is a diffuser, so there is no work interaction, so work in and also work out here is equals to 0. Okay, and then we have a Q in here, so this is Q in, Q added, okay, because it is gaining heat, so Q out is 0. Okay. Okay, another thing is that even though the question does not mention that we can neglect the potential energy, but when we read the question, there is no such value for elevation, okay, for Z. So even though the question does not mention, we can assume, okay, we can assume that the potential energy can be neglected. Okay, because we don't have any values which represents the potential energy. Okay, so we can assume that potential energy can be neglected. Okay, so now we can proceed with step 1. Okay, so we have step 1 here, which is to draw the schematic diagram. Okay, our understanding, based on the question. So for a diffuser, okay, make sure you draw it properly. The diffuser, the inlet is smaller than the outlet. So, okay, so make sure you get your drawings right. Okay, so state 1 on the left and also state 2 on the right. So the refrigerant will flow, okay, through the diffuser. So the substance is R134A. Okay, so we can then write the properties. Okay, so at state 1 we know the temperature 22 degrees Celsius, okay, if I'm not mistaken, and also we know the phase saturated vapor. Okay, and that is about it. Okay, at state 2 we do know the pressure, okay, 700 kilopascal. Okay, we do know the temperature, 40, okay, degrees Celsius. We do know the velocity, okay, 82 meter per second. Okay, so these are the properties. Another thing we can label, okay, don't forget to label the Q in, okay, because it is gaining heat, so Q in here. Okay, so 5 kilojoules per second. Kilojoule per second is another unit for kilowatt. Okay, so we can write it like that. And another thing that we can also write is the relationship between the inlet area and the exit area as stated in the question. Okay, so the exit area is 1.85 larger than the inlet area. So if we were to write it, okay, in terms of an equation, so it will be the exit area is 1.85 greater. So meaning that for A2, it is 1.85 greater than A1. Okay, so this is the relationship equation between the exit area and the inlet area. Okay, so we can also write that down. Okay, so now for step 2. Okay, so try to write the required equation. So for the first item, we need to find the velocity, okay, at state 1. So the first option is to try and look at the mass flow rate equation. Okay, since what? Because why? Because we have the term for velocity in this equation. Okay, so we can try to look at it first and we can check on the values. So we don't have mass flow rate, so that's one unknown. Okay, we don't have the velocity. Okay, that's two unknown. So when we have two unknown but only one equation, so automatically this equation cannot be used. Okay, so next, okay, what is the next option? The next option is the conservation of mass principle, or the continuity equation, which we know is the mass flow rate at the inlet is equals to the mass flow rate at the exit. Okay, so when we expand this equation, okay, as follow, we expand the equation. All right, and then using this understanding here, okay, okay, we can try to substitute. So A2 is 1.85 greater than A1. Okay, so here we have A1. Oops, sorry, here. Okay, and 1.85 greater than A1. Okay, so V2. Okay, so on the left hand side we have A1 and on the right hand side we have A1. We can cancel, so what we are left with is an equation. Okay, velocity, specific volume, state 1, 1.85, velocity state 2, specific volume state 1. Okay, so when we check on the values, we have to find V1. Okay, we have to find V1. For specific volume 1, we can find it because we know it's a property at state 1. Okay, so later in step 3, make sure we can find the specific volume at state 1. We do have V2, velocity at state 2, and same as specific volume at state 1 just now, so we can find the specific volume at state 2 because it is a property at state 2. Okay, so when we check on the values, okay, some values we are required to find later, and we have the velocity, so basically we can solve for the velocity at state 1 using the conservation of mass principle. Okay. The next item is to find for mass flow rate. Okay, so the next item is to find the mass flow rate. Okay, the first equation we should try to use is the mass flow rate equation. Okay, but when we look at this, let's say we want to find it at state 1. Okay, so mass flow rate at state 1, area at state 1, velocity at state 1, specific volume at state 1. Okay, so this is one unknown we don't have because we have to find it. Velocity at state 1, if we solve for the first item, we have already calculated it. Okay. Specific volume at state 1 also we can find because it's a property at state 1. But for area at state 1 here, we don't have the value. No value. We only have the relationship which states that A2 is 1.85 greater than A1. We only have the relationship, no values. So basically A1, we don't have the value, so there are two unknowns here. So automatically this equation cannot be used. Okay, one equation, but we have two unknowns. So what is the next option? Okay, the next option which has the term for m dot, okay, mass flow rate, is the SFEE. Okay, so we can try to use the SFEE. So we have to write down the general equation first. Okay, on the inlet side. Okay, and then on the outlet side, or the exit side. Okay, so the SFEE, you should memorize it. Okay, there shouldn't be any problems when writing the SFEE. Okay, general equation, and then we can cancel based on the condition. So Q in we cannot cancel because there is heat added. Okay, but we can cancel the work in because there are no work interactions. So work out. We can cancel for work out. Q out. Okay, because only Q in is available. And then we have assumed that the potential energies can be neglected. Okay, so what we have remaining is the on the left hand side we have the Q in m dot H1 plus the kinetic energy, and on the right hand side we have the m dot enthalpy and also the kinetic energy. Okay, so what we do next is since we want to solve for mass flow rate, we gather, okay, or we pull together, okay, all the terms with the mass flow rate. Okay, so since Q in has no mass flow rate, so it will remain on the left. Okay, and all the terms with the mass flow rate we put it together on the right hand side. Okay, so factorize the mass flow rate. So mass flow rate is on the outside. Okay, so be careful with the brackets. So H2 minus H1 here, and then plus with V2 minus V1 square over 2000. Okay, so be careful with the brackets. Okay, all right, so this equation, okay, so when we check on the values, okay, and we check on the values, we have Q in given in the question. We want to find m dot, so that's one unknown. For H2, we know that it's a property at state 2, so we can find it later. And then we have H1, this is also a property at state 1. Okay, we have velocity at state 2. And if we have solved for the first item, we have calculated for velocity at state 1. So all of the values required, we have either find or calculated. So there's only one unknown here. Okay, there's only one unknown here. So we can use this equation to solve for mass flow rate. Okay, so next is step 3. So for step 3, we try to find the required properties. So we start with state 1. Okay, so state 1, we know the temperature, 22 degrees Celsius. We know the phase set vapor. Okay, so using table A11, temperature table for refrigerant R134A, at 22 degrees Celsius, okay, since the phase is set vapor, so specific volume is same with Vg. Okay, so looking at the table, 0.033828. okay, meter cubes per kg. And also the enthalpy, okay, is Hg since it's saturated vapor. So looking at the table, 64 kilojoules per kg. Okay, so those are the properties required at state 1. Next is the, okay, so state 2, we try to do it here. Okay, so state 2, pressure is 700 kilopascal, or in megapascal 0.7, just in case. And the temperature is 40 degrees Celsius. Okay, so we don't have the phase, so we have to check on the phase first. So using table A12, since we have the pressure, 700 kilopascal, we are going to compare the temperature with the saturation temperature. And when you look at the table, it is greater. Okay, so the phase here is in the superheated region. So for superheated, okay, we have to look at table A13. Okay, A13 for refrigerant at 0.7 megapascal, 40 degrees Celsius. Okay, if we can read it directly, we will read it directly. If we cannot, then we have to interpolate. Okay, but I think we can read it directly. So we can read for enthalpy at state 2 here, and is 278.57 kilojoules per kg. And also don't forget to read for specific volume. Okay, so specific volume is 0.031696. Okay, so that is for state 2. Okay, so finally for step 4, what we do is we substitute and solve. Okay, so step 4 is to substitute and solve. So using the first equation just now, okay, our continuity equation. So velocity at state 1, specific volume at state 1, 1.85, velocity at state 2, specific volume at state 2. Okay, so either you rearrange or you just put in the values. Okay, so it's up to you. So specific volume at state 1, 0.0338828, okay, equals to 1.85 multiplied with velocity at state 2, 82, and specific volume at state 2 is 0.031696. Okay, so we can solve for velocity at state 1 here, and we should get around 161.9 meter per second. Okay, so depending on your decimal points, okay, so you might get slightly different answers. Okay, so be careful with your decimal points. And then finally, for our mass flow rate from our equation, Q in equals to m dot. Okay, be careful of the brackets, H2 minus H1 plus. So this was our equation just now. Okay, so we can always write it down back. Okay, so for Q in, okay, we only have to put in the value 5 here. Okay, remember the unit is in kilowatts, so we don't have to write it as 5,000. We only write it as 5. Okay, because all the terms in the equation, the unit must be in kilowatts. So for Q in here now is only 5 kilowatts. Okay, so m dot we want to find. Okay, so the change in enthalpy for state 2 is 278.57 just now, minus with enthalpy at state 1, 262.64. Okay, plus the change in kinetic energy, so 82 square, 161.9 square over 2000. Okay, be careful of the brackets. Okay, so solving this, okay, hopefully if I'm not wrong in my calculation. We should get 0.808 kilograms per second. Okay, so this is the answer for the tutorial question in chapter 3. So I hope all these questions can help you in understanding more regarding chapter 3. So thank you for your attention and have a good day.